So product rule, as I had just done, I'll put this one actually in the video. We did f of x equaling x plus 3 times x plus 2 and said, hey, wait a minute, but that equals x squared plus 5x plus 6, which we can easily take the derivative of using our power rules we learned. Okay, not a problem. So what happens if I'm multiplying two things together that I can't do that with? So for example, what if I had I don't know why that did that. What if I had f of x equals something really simple? X squared times e to the x. You know how to find the derivative of x squared, right? You know how to find the derivative of e to the x. And if, big difference, and I want to point this out, if I gave you that's a really easy problem, right? Do we agree? F of x equaling x squared plus ex, e to the x? Yeah, what is that? Yeah. F prime is 2x plus e to the x. And when your terms are multiplied by like that, perfectly fine. Use your power rules, you're done. Notice though, when they're added like that, these are being multiplied. Okay, you cannot. It's not 2x times e to the x. So I'm not even going to write that down. So you don't even want to see that. Pretend I even said it. Okay? In this case, you have to use something called the product rule. I'm going to give it to you using f of x and g of x. And then I'll show you another notation that our book doesn't use. But if you're one of those people who like to go look up things and find other people like Khan Academy that teaches you, there's other notation that could be used as well. All right, so let's suppose f and g are both differentiable at x. They're good functions and they're differentiable. The derivative of f of x times g of x. And that's kind of what I have with my x squared, right? Differentiable. Sorry. If I put my hand on it, I lose certain things. I'll get there. I'll get really good at this by like March, maybe April, maybe the first week in May. So here's how it's done. It says, see the f of x function? Go ahead and take the derivative of that one, multiply that by the regular g of x function, and then you're going to add that to the regular f of it. You're going to do the opposite. You're going to add that to the regular f of x function times g of x. Okay. An alternative notation. Why I like to introduce this alternative notation? Because you're going to see it as you progress further into Calc 1 and Calc 2 a lot. So I like to kind of get you used to seeing it now. But I don't care which notation you use. Alternative notation is saying, hey, U and V. You have two functions, U and V, and we're going to let Y equal, well, we only have to let Y equal. Let's have two functions, U and V. These functions, again, are differentiable. So the derivative of U, V together is U prime V plus U V prime. Okay. Do you see? It means the same thing. It's just different notation. It's letting U equal the first function, V equal the second function, just finding. It's a shortened form, but it is something that you'll see so much of. We even have something in integration called the U substitution that goes back to these U's and V's. So it's kind of good to see it. Mm-hmm. Yes, that means at X, your function's smooth, right? It's not some point where you can't get a slope. That's kind of what it means graphically. You can actually get a slope at X. Okay, and X could be anything. It doesn't matter. All right. So let's do that example. F of X equals X squared plus e to the X. So I'm going to tell you why personally I don't like F of X and G of X notation. Because students, but this, did I write plus? Let me stop that. Let me fix that. There we go. Because students see F, but that whole thing's F of X. No, you can break that F of X into an F of X times G of X. That's why I like to work with the U and V notation. It depends on what instructor you have in calculus, what notation I like to work with. All right? Don't get caught up in notation. The idea here is we need to start off with the derivative of the first function times the second function plus the first function times the derivative of the second function. Does that make sense? So in other words, start off with, let's do, what is the derivative of X squared? You multiply it by the full second function, e to the X. Then you do the opposite. Keep the first function, which is X squared, and multiply by the derivative of the second function, which happens to also be something like that we can clean up a little bit when I see that, because I see a common term. So you might, and again, how you do it in Math Lab, read that I think it's usually like in blue, italics or something. It tells you how they want your answers. This is also the same as saying e to the X, right? Okay, both answers would be correct, like on a test or a lab. Don't worry so much about that. So now, let's take a look at that one we did at the beginning of class, and let's apply the product rule and see how that was probably easier to deal with, but we can still apply the product rule. So the one we did in class was x plus 3x plus 2 Okay, so let's keep it like that, and let's apply the product rule. So if I were actually using u's and v's, all I would do is simply call, right, x plus 3 my u term, and x plus 2 my v term, right? You don't have to. You can call them separately f of x and g of x, whatever you want to do. So then, to find the derivative, I need the derivative of u. So I'm going to do u prime v plus u v prime. And what's the derivative of u? It's pretty easy. X plus 3. What's the derivative of x plus 3? It's the derivative of x plus 3. 1. I knew you knew what it was. It's 1. And then v plus, we simply write out u, correct? And the derivative of v. What? Okay. So work it out. It's, what's it? It's x plus 2 plus x plus 3 is 2x plus 5. It's not that much more, but 2x plus 5, 2x plus 5, doesn't matter which way you go, it works. So let's do one more example of product rule. Find a fun one. I'm just going in the book now. So many of them are all quotient rules. Here's an example. Do d dx I like this one because it tells you when do I have to use the product rule and when don't I have to use the product rule. All right, d dx of 6x minus 2x e to the x. You got to recognize what you have. First of all, that plus and minus, that can be separated out. Okay? Where's the product in this particular problem? Oh. Yeah, here's the product. Just here. This is not the product. So there are rules in differentiation that say, hey, wait a minute. I can do this. That's the same as saying so recognize where you need to use the product rule. Do I need the product rule in that first differentiation? Nope. d dx of 6x is what? 6. That's just 6. But put the minus. Let's put everything we do inside so we don't forget that minus sign. Now I got to use the product rule. So start with derivative of the first term. What's the derivative of 2x? 2 times and then what do I put down next? 2x, right? Remember, derivative of the first product times the second product plus, now you got to write the second product, so you got to write that 2x. And the derivative of e to the x, which is e to the x. Don't forget the 6 minus. So the answer is actually 6 minus 2e to the x minus, right, 2x. As you learn more derivatives, like of e to the 5x and stuff like our trig functions, there's more examples we can do here. Yes? I mean, if you can factor the 2, I would mark both of them correct. But factoring the 2 out doesn't do anything. Here's when you would do that. If there was something in the denominator you had to cancel it with, like when we move on now to the quotient rule. But since there's nothing to cancel, even that other one we had done, it didn't. When we factored out the e to the x, it's more cosmetic, I guess is the word, than necessary. Okay? Again, we will circle back to product rule as we get into more derivatives we can take, like especially our trig functions that we're going to look at today as well. So now what happens with quotients? Also, for those of you, this is Calc 1. We don't do a lot of proofs in Calc 1 at all. All right. The reason being is some students take Calc 1, they don't take any more math. Other students move along. So I do like to point out the proof of this actually comes from the limit definition. It is on page, for those of you who want to take a look at it, page 163 of text. And it actually comes from this. I'll write it out, but we're not going to go through the whole thing. It comes from taking d dx of f of x times g of x and using the limit definition product. So taking that limit as h goes to 0. So usually when we do proofs of derivatives like this, it goes back to that full limit definition of doing f So do you see how the limit definition changed? Instead of just f of x plus h minus f of x, they're multiplied together. So something you might want to do is think about that on your own. And if you want to know, because we're not going to take class time to do it, check out page 163. How's that? Okay? Same's going to go for the quotient rule. So let's do the quotient rule is a little more complicated. Sorry, I know, I scooted it. It comes back. I'm learning that if I just be patient, it always comes back. There we go. And of course, the quotient rule has to change things up a little bit. So now I'm going to do d dx. Oops. Made that way too big. I thought putting the lines up there would actually help me keep it straighter. I'm not sure that's happening. So here what was cool about the product rule. When you did the product rule, because, do you remember the word commutative? Anybody remember what the word commutative means? It's like one of the first things you learn, like in middle school when you're learning algebra for the first time. Nobody knows what the word commutative means? Commutative simply means that 3 plus 2 is the same as 2 plus 3. Do you remember that now? No? No? You can switch in addition, right? Right? So when we did, let's take a look for a minute, the product rule, would it matter if I put this part in front of that part? No, because they're adding together, right? Because we all know 3 plus 2 is the same as 2 plus 3. That's called commutative property. Does it work for subtraction, though? No. So here's where it gets funny. Product rule, you can get it right if you accidentally put this one out front, add it to that one. You can still get it right. Doesn't matter the order you do it. In fact, when I'm doing it on the board, sometimes I'll do it the other way. But the quotient rule, it's going to matter. All right? It is important you follow the order on the quotient rule. Because the quotient rule says we're going to start with the denominator. And we're just going to simply write, oops, I didn't write it. We're going to write g of x. So you kind of have to get in the habit of taking what's in the denominator and just write that down first, exactly as it is. Now you're going to take the derivative of the numerator. And then you're going to subtract. That's what's telling you you can't reverse that. You'll get the whole thing wrong. And then, of course, you're going to subtract what? Yeah. Now, what doesn't matter, this is where commutative property comes in again, is 3 times 2 the same as 2 times 3? Do we agree? Yeah, so you could put the f prime for, like, that part doesn't really matter. However you want to memorize it your way. And then we're not done, because it's a quotient. Those of you who've done this before know what goes on the bottom. You remember? You're just going to square your g of x term. Just square your g of x term. That is a g. Don't look like a g. Let's make that look more like a g. There you go. Okay, that's your quotient rule. This one gets a little... Yeah, some of these answers, we need to work on the lab on these. There are a couple where I say, just write it out. Don't even try to simplify it. They get a little more complicated. But let's start with a nice kind of simple one. Well, let's do this. Let's start with a really, really simple one and say, well, how would I use the quotient rule on that? You know what the derivative of e to the x is, everybody, right? It's the easiest one in the world. It's the only one where the derivative is itself. E to the x is e to the x. What if, though, I wanted the derivative of e to the negative x? Now, if you've taken calc before and you know the chain rule, which we're not doing till next week, you can do this a different way, but I'm not doing chain rule right now, okay? Do you think that's just e to the negative x? What do you think? No. So, where does the quotient rule come in? Remember what we said in the beginning class? How can I rearrange this? First of all, okay, when you're saying, I know e to the negative x actually can be written how? The second you put something in a fraction, you can use a quotient rule. It's a fraction. There's a quotient rule there. So let's do it. You want to take a guess of what you think the answer is before we do anything? E to the negative x, derivative of e to the negative x. maybe it's e to the negative x, right? Anyone else want to take a guess? Now again, if you know chain rule, you already know what to do. But no guess, just a guess. Yeah, no idea. Two. No other guesses. Negative e to the negative x. Any other guesses? So let's go through the quotient rule on this particular one. This will actually be a more common one. You will be able to do this one in your head without a quotient rule, I promise, by the time you're done. But let's do it on here, because quotient rule can be applied if the function in the numerator is a 1. It can still be applied. All right, let's just go through the steps. So I'm going to label f of x is just the function 1, right? And I'm going to label g of x is my e to the x function, all right? So that's how I'm going to label them when I work it out. So let's do it. I start with g to the x. Well, that's e to the x. All right. So I have g to the x. Now I have the derivative of f. Well, what's the derivative of f of x, everybody? What's the derivative of 1? I'm seeing some of this. Yes, it's 0. So it's a constant. 1 is a constant. It's just 0. A lot of stuff's going to go away in this problem. Don't forget your minus. All right, what is f of x is 1. Oh, what's the derivative of g of x? This one I know you know. E to the x. And now I need e to the x squared. Well, we got to do a little work. Not much, just a little bit. Just want to make that shorter. Okay, well, that's 0, right? That's just a 0. So I have negative e to the x over power raised to a power. What's e to the x squared? Yeah, e to the 2x. This is very similar to having, you know this. What if you had x squared over x cubed? They cancel, right? Right? This is saying I have an e to the x times another e to the x. So doesn't one of the e to the x's cancel? One of the e to the x is going to cancel, so I'm left with negative 1 over, which can also, if I wanted to flip it up, isn't that negative e? There you go. Yeah. So again, multiple methods for doing this. You will learn another one, a quicker one. But I wanted to go through the quotient rule with this one. Something seemed kind of simple, but it works. All right, so let's go to some polynomials. Because here's the thing with the polynomials, you can't always. Yeah, we'll do this one. All right, let's do a function. I'm going to do a few things with this function. First, I'm going to just find the derivative. So f of x equals x squared plus 1 over x squared minus 4. Sorry. My husband's one of those people that has like cameras over every inch of our house. A squirrel goes by sometimes, too close to it, and it goes off. X squared minus 4. Okay, so first, let's just find the derivative. Let's use quotient rule and find the derivative. So again, I'm purposely using f of x. I don't want you to get caught up with notation. As long as you recognize, don't worry about notation, because I can write this using u's and v's also, right? I can actually write that using u's and v's. If it were u over v, it would be v u prime minus u v prime divided by v squared. So you can do it with u's and v's as well. All right, quotient rule. I'm trying to keep it all on the same page. There, we can do it just down. You can do it down there. All right, so f prime of x. So what do I write down first? Okay, what you need to remember is g of x is the denominator. So just write your denominator first. Let me do this because these are going to get more complicated. So sometimes off to the side, what I do is just jot down what those derivatives are. This way, when I'm putting them into my problem, they're already done. Does that make sense? Because what if finding the derivative of the other piece is more complicated? So I'm going to do that, and then I'm going to real quick do d dx. Aren't they both 2x? Right? Both derivatives are 2x. Okay. So I have my g of x times the derivative of the numerator, which is 2x, minus your numerator times the derivative of the denominator, 2x, all over g of x squared, which is the denominator squared. Okay, so let's simplify this up, because this is only part 1. I'm going to add a part 2 to this problem that's going to circle back to what we did last week. This is just part 1. All right, let's work this out a little bit. What is 2x times? You got to distribute. You need to simplify. You got to do the work. 2x times x squared, 2x cubed, right? Yeah. Minus, I'll do it, just check me. And guess what the number 1 mistake in using any quotient rule is on a test? Yeah, you forget to distribute the negative when you in the subtraction part. Because this is actually 2x times x squared, but it's minus. So it's going to be minus. But it's also, so look, it's this. That minus needs to get distributed to both pieces, so it becomes minus 2x, correct? And let's just keep this as it is. Don't FOIL things out until you find it absolutely necessary in the problem. Simplify it some more. Oh, look what happens. What does it become? Here we go. That's my derivative. Okay, so let's not forget why we find derivatives. I'm going to add a second part to this problem. Part 2. Which if you're only given part 2, you have to go through and do part 1 regardless. Remember that. So here's what I want you to do. I want you to find the tangent line of the f of x. Oops. So you can't just say find the tangent line. You have to find the tangent line in order to find a tangent line, because remember, f prime of x represents whatever this curve is. What is it? X squared plus 1 over x squared minus whatever it is. All right, whatever this curve is. This is the general tangent line anywhere. That tangent, that slope is going to change, right? It's not the same here as it is there, correct? It depends on what the x is. Remember that. The actual tangent line, the actual slope is going to change depending on where x is. So I want you to find it at the point So you can't find a tangent line unless you're given a point to find it at the point 3, 2. All right, to find a tangent line, which is a linear equation, y equals mx plus b, tangent lines are always linear equations, you need two things. You need a slope and a point. I've got a point. I have information about my slope. How do I get the actual slope? By doing what? So what am I plugging in? What number? In this case, 3. You're plugging in the x value. That's how you're going to get your slope. So your slope at 3, 2 is going to be the f prime of 3. In other words, you're going to calculate that derivative when x equals 3. You do the math. You don't need to copy my math because my math tends to be wrong. I'm cheating. My math is correct. There we go. Okay. So again, let's not forget why we find derivatives. Ultimately, whatever this looks like, which is more like this, because it's got asymptotes and all sorts of stuff going on. It's kind of, it's a funky, something like this. Okay. So now I have it narrowed down. Oh, I want, 3. It's not drawn to scale very well, but you get the idea. I want that tangent line. Okay, that's the tangent line I want. I'm almost there. I've got a slope and I have a point. And what's that last step you need to do? We went over this last Tuesday. No, you took a test last Tuesday, didn't you? We went over this last Thursday. I have a point. I have a slope. There is a formula called the point slope formula. Remember that? Use the point slope formula. So y minus 2 equals negative 6/5 x minus 3. And just, okay, that is good if MATLAB accepts point slope form. I don't know what MATLAB's going to accept. They'll accept different things, probably for different problems. You got to read the print. That's where you don't want to get frustrated and put, you got it wrong, not because you got it wrong, because you put it in the wrong form, because you didn't read, right? Hopefully you're learning that in MATLAB if you haven't already. Or you do this however you want to solve it. If you do the math and rearrange it, it looks like this. It ends up being 28 out of 5. Because you got to distribute, it becomes 18/5. And then you got to add 2 to 18/5. Yeah, when you add 2 to 18/5, you're adding 10/5. So 28 out of 5. That's it. Just do some fractions in your head. Okay. I'm going to make you suffer through one more. And then we are going to do a little bit with our trig functions. Because real quick on the lab, you're going to have to do the trig functions. Trig functions are cool. Mostly memorization. But that's the one I want. Oh, yes, a good one. You ready? Last example for today. Well, for this section. Not for today, for this section. So, I want the derivative tell me what we're using. What are we using? Definitely a quotient there, right? But there's also a what? Yep, you're using both. There's a product and a quotient. So this is one of those examples where it's kind of good to figure out the derivatives off to the side first. So this is why I like that UV kind of notation. So let me show you the UV notation again for quotient rule. The UV notation would be, okay, I want the derivative of U, right, divided by V. So if I do what I know about quotient rule, it would be V U prime minus, right, okay. So take a look at that and make sure that makes sense with your f of x notation and your g of x notation. Does that make sense with your f of x and g of x notation? Are we on the right track? Because the g of x gets squared, the g of x gets started up there, that's your v. All right, so, oh, okay, v u prime minus, and then just switch it, u v prime. The reason I like to do that, because then I can say, okay, looking at this problem, because it's going to get a little complicated. When you got to embed one method inside of another, it starts to get complicated. That's why I like to do a little bit off to the side first. And I'm going to let u, of course, be the 4x e to the x. So that means I need to figure out what the derivative of that is. So let's just calculate the derivative of that, simplified, and get that part done. So let's figure out u prime. Well, this means I now need a product rule for u prime. All right? If you try to do it all within the problem, you can do it. It just gets a little, sometimes it gets really messy. So I'm going to do it this way. So what's u prime? So this is now we got to go back to product rule. Product rule says, oh, I'm just going to do 4x times the derivative of e to the x, which is, and then switch it. What's a derivative of 4x? Okay, are we good with that? There's nothing we can do to simplify that, is there? It's just simply 4x e to the x plus 4e to the x. And then, of course, v is x squared plus 1, but that one's easy. V prime is just 2x. Okay? So I'm going to use this, and now I'm going to do my quotient rule. So I did my product rule off to the side, now I'm going to do the quotient rule. I don't know why I put an equal to sign there. Don't put an equal to sign there. That was dx of that. Anyway, so now look, I start with my denominator, which is just x squared plus 1. Now I need the derivative of the numerator. We found the derivative of the numerator. Here is the derivative of the numerator. You see that's already done for you. So let's go ahead and put it in the problem. Minus the numerator times the derivative of the denominator, which is my v prime. All over we can actually simplify this up a little bit. We are going to simplify this a little bit by first distributing everything and then factoring out what we can factor out. Okay? This one's not too bad. Plus, it's a little messy. It is a bit messy because you got to FOIL, but we can do it. You ready? You got to FOIL x squared plus 1 times 4x e to the x plus 4 e to the x. Do you see that? So let's do it. So isn't that 4? Yeah. Because there's not another one over here. This minus sign says I can't cancel these. Yeah, this thing. So you can't cancel across like a big plus or minus. Okay. You could if there was an x squared plus 1 over in this. So we got to FOIL. Do it carefully. X squared times 4x, so that's 4x cubed e to the x. Now I'm going to do x squared times the other one, which is 4x squared e to the x. Everyone just follow me on each so we make sure we get it correct, because it's so easy to make a mistake. Now I'm going to multiply the 1 by everything, right? So that's going to give me 1 times 4x e to the x plus 1 times 4 e to the x. Luckily, the second term doesn't need to be FOILed. It's simply there is a squared. Sorry about that. Thank you. Yes. There is actually something you can factor out, and there's something I don't think you can. None of them could be combined, right? Because this one has an x cubed. Wait, this one. Can this one be combined? Yeah. Yeah. This one and this one could be combined. Are they the only two that can be combined? Do we agree? So we do get minus 4 . You know what's wrong with this problem? It's all very similar each term, right? And what can be taken out? A 4e to the x. 4e to the x can be taken out of every term. Leaves me with x cubed minus x squared plus x plus 1. So none of this, after you set this up, you've actually done everything new. Everything beyond that is pretty much, I hate to say it, basic algebra. You agree? Yeah, it kind of is. It's tedious. Some of them are a little tedious. But it's basic algebra. Okay? So, I want to at least get to some sines and cosines today as well. All right, so I'm going to go for about another 20 minutes, and then I'll get you into your lab groups. And you will see on the lab, some of them are insane, and I don't make you simplify them. I make you get to this step and stop. Just so the setup. I make you get to the setup. All right? But none of these would be fun. They can be much more fun if I can add sines and cosines to them, right? And tangents, and secants, and cosecants, and cotangents, right? You don't agree? Let me pop one thing on real quick. This is in your modules. Has anybody looked at it yet? Okay. Here's what I want to make sure. You've got to know this. Know your reciprocals. Because when we could talk about simplifying trig functions, sometimes using reciprocals comes in handy. All right? Know what's reciprocal of what. Know your tan and cotan functions as well. Pythagorean. A lot of this other stuff will come into play if you want to actually go over the proofs we're going to do. So think about this for a minute. Remember what the proof, what do we go back to prove any derivative? We go back to that limit definition. Do you remember the first part of the limit definition? It is f of x plus h, right? Well, think about if I turn that function into a sign. I'm going to do sine of x plus h. Where do you think you're going to expand sine of x plus h? Right here. So a lot of this stuff comes into the proofs, but definitely you got to know those reciprocal identities. All right. I do want to put this at least on a separate, there we go. So 3.5. I'm not going to do proofs though so much as I want you to understand the sine function graphically. I think it's way more fun. And I want to start with the most basic, which is simply the derivative d dx of sine x. So the formal algebraic proof for this derivative does use the limit definition, and that is on page 173. I'm not going to do the formal proof. We're going to have more fun with it. And we are going to go back to what we went over in 3.2 to also refresh, in which case I'm going to go Desmos. So if you have your computer, go to Desmos. If not, I'll do it up here. And I'm going to start with just the sine function. I'm going to get myself a nice interpretation so that everybody can see it. I like to have sine functions in there. It just bothers me. I like to have it in in radians. I don't like it in decimal. It has to be in radians to work with it. All right. So do you remember back in 3.2, that was the video I screwed up and I still don't have it uploaded in my online course, which you'll hear me on here. I promised them a video for 3.2, so I got to get that done like later today. So there, I said it on the video, so now that'll force me to do it. We talked about the relationship between a function and its derivative, the graph of the function and the graph of the derivative. Remember that? And we said, okay. Get this nice and big here. I can't write on there, of course, but that's okay. So sketch yourself on your paper a nice little sine function. Just a simple little sine function like I have here on the board. Desmos has to make it so you can get your stylus and write on top of it. It really does. So the derivative function represents the slope at every point, right? Okay? What are the easiest slopes to see in any function? We talked about this last Thursday. The zero slopes, right? So where is there a zero slope? Where can I draw a perfectly horizontal line that represents the tangent line? Yeah, one's right there. That has zero slope. And doesn't this have zero slope? Okay? So that means my derivative function everywhere the slope is zero is actually going through. So in black, I'm showing the derivative function. Everybody see that? Where else is it zero? Here? Okay, so my slope's going to go through there. Something else to remember. This slope between negative pi over 2 and pi over 2 is always what? Positive. So that means it's going in the positive direction, right? Until it gets back down to here. The other thing I want you to note is look right here. If I were to draw a tangent line, what do you think the slope of that particular line right there is? Perfectly 1. Believe it or not. So that means I need to come up and stay positive. And then what happens to my slope here? It's got to be under the x-axis because it's negative, right? What function did I just draw? The cosine function. Let me get rid of my black. Do you see graphically how it makes sense that the derivative of the sine function is the cosine function? Okay? And if you want the proof, you can go to that page in the book. So the derivative of sine is simply cosine. Let's write that one down, memorize it, know it. Now, don't make assumptions. I want you all on your paper to sketch yourself a cosine function. Go ahead, sketch it. You can do it. So we're good here. The derivative of sine is 100% just cosine. But now I want to find what is d dx of cosine of x. And I know you're all thinking what? Well, it's got to be sine, right? Well, maybe, maybe not. Let's take a look. So give yourself just a nice little sketch of a cosine function. So your cosine function at 0 starts where, by the way? Up here, right? Went too far. Let's try to get this as accurate as possible. So here's 2 pi. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4. Here's pi. Let me put some stuff in here. So get yourself a nice cosine function. Looks like this. Now go ahead and on your paper, sketch yourself the derivative of that function, kind of like we just did. Think about the derivative of that function. Go ahead and sketch yourself the derivative of it. Sorry, I keep losing mine, but you won't lose yours on your notebook. Keep losing mine on here. There we go. So here's my first question. Did you try to sketch yourself kind of like we did before? Putting where your zeros would be. Right, 0, 0. And knowing when it's negative and knowing when it's positive. Is it, here's the big question, is it the sine function? Is the derivative of cosine sine? Yes or no? What do you think? Did you sketch it? So from here to here, I'm definitely negative, right? Aren't I negative? This is negative. And then what happens there? Then it goes positive, right? Look at that red line. Is that the sine function? Everybody. No. Is it close to the sine function? In fact, it is the sine function. So d dx of cosine. So there's your first two major derivatives. The derivative of the sine is the positive cosine function, but the derivative of cosine is the negative sine function. You just got to memorize that. And if you don't memorize it, sketch it. If you get stuck and can't remember, just sketch it. See how we just did that? Or learn the whole limit definition with sine and cosine. I'll let you look at the book for that one. Page 173. All right. So we're good there. You know the derivative of sine now. You know the derivative of cosine. Let's move on to tangent. We're going to do this one a little bit differently. Because ultimately, you're just going to memorize these trig derivatives. Let's do tangent. We're not going to use graphs for this one. We're going to rewrite tangent. Because you know how to rewrite tangent. Using what we just did. Can I rewrite tangent just using sines and cosines? Yes, I showed it to you in the little reciprocal things, right? So that is the same as d dx of what? How do I rewrite tangent? Sine x over cosine x. Remember that? And now, hey, I know the derivative of sine. I know the derivative of cosine. And I know something called the quotient rule. So guess what I can apply here? Quotient rule. Because if you don't memorize this one, you're going to have to do the quotient rule every time you see it. So we're going to do it once. Then you're going to memorize it, right? Let's do it. Quotient rule. This is good because it'll let us practice. right. Quotient rule says I start with, what do I write down first every time I do the quotient rule? Denominator, which is cosine x. Then I want the derivative of the numerator, and we already said what the derivative of sine is, right? What's the derivative of sine, everybody? Right? Here, I'll put this on top so you know where it's coming from, because you want d dx of sine x, right? Which is cosine x. All right? Then I need a minus. Now I write my numerator, which is, my numerator is sine x. I already write cosine x, so I write sine x. Times, now I want d dx of cosine x, which is a negative sine x, right? All over. What goes in the denominator? What goes in the denominator? Cosine squared x. Okay, let's clean up the numerator. Let's clean that up. Cosine times cosine is simply, oh, I got a negative times another negative. What does that make my numerator then? Did everybody see that? I got a negative times a negative, so that's going to make that a positive. And what's sine times sine? Again, and this is huge common mistake. Huge common. You cannot cancel those cosine squared. Because the big plus sign right there. But what is cosine squared plus sine squared? 1. But I'm not going to leave it as 1 over cosine squared x because I don't like fractions. What's the reciprocal of cosine? Secant. And since it's squared, there you go. They're the only ones that are going to be, I'm going to give you the other 3. I'm not going to take you through anything with those 3. So let's write out all of our trig functions now, because again, I'm just going to give you the other ones. Yeah, I really am. It's going to come back, watch. It's going to come back. Yes. Okay, here we go. So, d dx, put them all together, of sine x equals cosine x. And d dx of cosine x equals negative sine x. Now we know d dx of tan x there is a nice pattern to some of these that'll help you memorize them, actually. We just found that one to be secant squared x. And you could literally, you can do all the rest of them using that quotient rule with the right reciprocal, by the way. We're not going to go through it, but you can. So underneath of that tan, and I'm putting these in this order for a specific reason. I promise you, it'll help you memorize them. So right underneath tan, do d dx of secant x. So to do secant x the long way, what's the reciprocal of secant? You'd have to do 1 over cosine and go through the quotient rule with 1 over cosine. And trust me, you will get secant x tan x. That's what you'll get. Now, cosecant and cotangent have a similar relationship as tan and secant have. So let that sink in for a minute. Cosecant and cotangent have a similar relationship as tan and secant have. Because remember, I'm helping you memorize here. So, having said that, they also have a similar relationship of cosine. Given all that information, what do you think the derivative of cotangent is? Want to take a guess? For those who don't already have it memorized. So it follows a pattern up and it follows a pattern over here. What do you think? Just guess. Be free to guess. Guess. There's not much left in terms of trig functions. Come on, I know some of you have something you want to say. Sine squared x. More guesses. Cosecant squared x. More guesses. Somebody, wait a minute, I heard something. Negative cosecant. Sorry, I get excited. So look, tangent is secant squared, so cotangent is cosecant squared. Cosine ends up with a negative derivative. Cotangent ends up with a negative derivative. Do you see the patterns? Now that you see the patterns, can you tell me what the derivative of cosecant x is? Take a minute. Follow all the patterns in my little chart here. You want to go for it? You missed one pattern. Yes. Negative cosecant x, cotangent x. And again, I'm just doing this to help you memorize at this point. So here's the things you notice, right? Any trig function that begins with a c has a negative derivative. Isn't that cool? Your tan and secant have the same relationship as your cotan and cosecant, except your cosecant and cotan, of course, are negative. The other thing I want to point out for my engineering students and my pure mathematicians out there, you will never, ever get rid of that. You will see that in every math class you take after that. Those are the most popular. Just letting you know. They're just used a lot. Okay. I'm going to stop. Well, yeah, well, one here. Here, do a simple. We'll stop there with those. We'll stop there with those, actually, because we did an example of sine over cosine and using quotient rule already. Okay, I will stop there. But now you get the idea. So I'm going to stop, and I can't bring myself to stop. So one more quick thing. You get the idea. So now you can do things like right? You can do things like that now. And you can use your product rule. We will do this one's quick. Well, you can use your product rule on something like that. Because you can say, oh, that's a product rule. So you get in the habit of using your product rule, which says, and you can use, product rule is a cool thing in that you can rearrange it, you can mess it up because it's commutative all around. Doesn't matter. But what's the derivative of x squared? Times sine x plus x squared. And what's the derivative of sine x? Done. See how easy that was? You can't even really simplify it. It's just done. Now I'm done with the lessons.